Hello, Year 10. Today's a test review. Most of you have done the assessment, which is great, and now I'm going to go through the answers. So, obviously you don't have to use green pen because you're at home, you might not have access to it, but if you are using, if you're editing your document, just change the font to green and put the answers in. Well, hopefully, since I said the word enough, we know that the answer to question 1 is an induced magnet. Part B. So it shows the 3 different types of bar, and it's asking which one is unmagnetized iron. Well, if you look, this one repels. This 1 and 3 absolutely cannot be unmagnetized iron, because only 2 magnets can repel. Well, that means that one's a magnet, and because you see that, let's say, this piece here, if this was a magnet and this was north and south and it attracted, if you flipped it to the side it would be south and north and it would repel. So that can't be correct. Because it attracts both way rounds, you know that this is a piece of unmagnetized iron. So it's bar 2. You could say anything like when you flip bar 2 it attracts both ways. So the same end of bar 1, so side, I'm going to write end B, this end here, attracts both sides of bar 2. So that must mean that bar 2 is a piece of unmagnetized iron. You could say that because bar 1 and 3 only magnets repel, and bar 2 doesn't repel anything, that is also the same answer. Okay, a student investigated the strength of different fridge magnets by putting small sheets of paper between the magnet and the door. Why was it important that each small sheet of paper had the same thickness? Now, you need to, well, whenever you do a test, you can only change one thing. Okay, there can only be one independent variable. Right? So in this test, the number of pieces of paper, okay, is your independent variable. If the thickness of the paper changed as well, that would be 2 independent variables, and your results wouldn't mean anything. So you could say every experiment needs only 1 independent variable, but if you said something on the sort of more common sense line, like the thickness of the paper would affect the results, there you go, that would get you the mark. You can't say to keep it a fair test. If you ever write the words "so it is a fair test," you get 0 marks on every single question. It's not specific enough. You need to say what part of the test is not fair. Well, you need to say that the thickness of the paper would affect the results, or you can only have 1 independent variable in an experiment. Right. The bigger the area of the fridge magnet, the stronger it will be. Give 1 reason why the results do not support the students. Well, it's the opposite, right? You could say the smallest fridge magnet was the strongest. Smallest area was the strongest, and the biggest one was the weakest. That one was quite straightforward. Question 2. Again, moving a magnet into the coil of wire causes a reading on the voltmeter because a potential difference is induced across the ends of the wire. So a student investigated how the number of turns of coils of wire affected the maximum voltmeter reading. Suggest 2 variables the student should control. Now, if we go up a bit, so what they've got a magnet, they move it into a coil of wire, and they change the number of turns. So the number of turns is the thing that changes. Everything else has to be controlled, right? So use the same magnet or the same strength of magnet. I'm going to put same magnet because If you change the magnet every time, it would affect your results. Now, if you put the number of coils of wire, that's not correct, because that's the thing that we are changing in this experiment. We are doing it with 10 turns of wire on the coil, sorry. Then we're doing it with 15 turns of wire on the coil, etc. So that changes. Now, remember from the the simulation that I showed you the other week, the faster I move this magnet, the greater the voltage that is induced. So another thing you would have to keep the same is the movement of the magnet, or the velocity or the speed of the magnet. You weren't given the same type of wire, that wasn't enough. It is something you have to control, but the mark scheme wouldn't allow it because there was many more important things. Another thing would be make sure you have the same pole of the magnet going towards the wire. So I prefer control the speed of magnet. You are allowed make sure the same pole of the magnet points towards the wire. Right. One of this results is anomalous. Suggest reading. Well, easy one. They misread the voltage, or they miscounted the number of turns. Really, I think the more likely thing is that the number of turns on the coil is miscounted, because that's the easy thing, right? You do 100 turns of wire on the coil, and instead you actually do 95 turns of wire on the coil. You miscounted, right? So you are allowed voltmeter misread, because these are the two things that have been counted, right? This is the independent one. This is the one you are changing. You counted the number of turns on the coil of wire, and then you read the voltmeter reading, the maximum. So there are two potential sources of error. Choose one of them. Voltmeter misread. Draw a line of best fit. I'll try and draw a line of best fit on this. It's not going to work very well because it's... Wait, oh, maybe it will. That's not bad. I gave you a bit of leeway with this one because you were drawing on a computer. It's quite difficult. I just got lucky that actually lined up. Sometimes it goes way off and it like ends up over here somewhere. But you can see that this is the anomalous result. So a data logger can automatically record and store data. It may have been better for the student to do this. Suggest one reason why. Well, you can save all the data and recheck it all. Is one thing, because it logs everything. It can take more readings in a given time, and if, say, I put the magnet in, and so you know when you have your magnet and you chuck it through the coil, right? You'll have the data logger here. It'll be recording stuff, and what you'll find is the voltage it'll do that, won't it? It'll have a maximum voltage. The data logger, because it logs the data here, 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 it does it like hundreds of times a second. The data logger is more likely to get the exact voltage correct. So you've got loads of different reasons. I'm going to put it is easy to identify the maximum voltage. Something that's probably a bit more obvious, the data logger can record more readings in a set amount of time. You were allowed, it's more accurate, but I'd be careful with stuff like that. So it can take more readings in a given time. If it was like a 2 marker, it would take more readings in a given time, so it is more likely to identify the maximum voltage. That would be a 2 mark answer, because they sort of lead on to each other. Question 3, I thought this was a bit cruel, but it's like a classic one where you've got to make sure you read the question properly, or look at the diagram properly at least. You can see that this is the person's thumb here. There's the person's first finger here, and there's the person's middle finger here. So if you held your finger up and went force field current, my thumb is, so obviously you can't see me, but right, I've got my thumb up here, like this. There's my thumb, there's my first finger, and there's my middle finger, right? I went force, field, current. Now, that diagram is not the same as this one. My current is the middle finger, my force is the thumb. So this is your force. My middle finger is the current, okay, and my first finger is the field. So it goes field, current, force, because they're holding their hand at 90 degrees. They're holding it kind of like, I don't know, sideways. So, draw an arrow on figure 2 to show the direction of the force acting on wire AB. If you said an arrow pointing vertically downwards, you got the mark. Now, I'm going to try and see, because again, you can't see my hand. I'm going to try and do this. So, if I have my force, field, current, like this, F, B, I, right, current's facing up. So, my current is going up. This is my current. So I've moved my middle finger to point along this direction of this red arrow. My magnetic field goes from north to south. It goes this way. So I've pointed my first finger that way. And as I point my first finger that way, my thumb ends up pointing downwards. So my thumb actually points that way. So you just try that now, please. Get your middle finger, point it in the direction of the red one. So it's kind of, I'm pointing it towards the screen. It's isometric, so it's kind of hard. Actually, this is going into the screen. My B is going to the right. My first finger is going to the right. My thumb is going down. So this is my force. So that is the direction that the arrow is pointing in. Now, this would, so part 2, suggest 2 changes that would increase the force acting on the wire AB. That word there, increase, you have to specifically say what change you do that would increase the force. You couldn't just say different magnet, different current, or different potential difference, whatever, because you need to say what would increase the force. So you need to increase the current or the potential difference. Okay, and you need to increase the magnetic field strength or the strength of the magnet. Okay, let's see if I can use a thinner pen, maybe it might make it easy to read. Suggest 2 changes that would reverse the direction of the force acting on the wire. So what do you have to do? You need to flip the poles of the magnet, or flip the magnet. Okay. And what do you have to do? You could flip the batteries. If you said flip the batteries, you'd get the mark, really. So reverse the battery or reverse the current. I prefer just saying reverse the current. Okay. Part C. Blah, blah, blah. And then it says calculate the efficiency of D. So here's D. How do you calculate efficiency? Well, efficiency equals, so let me think about this, it is the output, so if you've got, you should have more in than you get out, so it's more, yeah, of input times 100%. Now let's have a look, because this fraction has to always be below 1, right? Unless you can't have something that is more than 100% efficient. For example, if I put in 1 joule of energy and I got 2 joules of energy out, okay, I would get a 200% efficiency, which can't happen. If you can get that to happen, then we've solved the energy problem, and you'll get a Nobel Prize. Okay, so my efficiency is this. Let's have a look. Output is here. So this is my output. So my efficiency equals 120 divided by the input. Where's my input? Input is here, right? 120 divided by 80. That times by 100. So this equals 1.5. Times it by 100, I get 150%. You got the mark for the equation. You got a mark for 150% or 1.5. If you put 1.5%, you didn't get a mark. So you got a mark either for this or for this. Comment on your answer. well, you can't have an efficiency greater than 100%. Have an efficiency of bigger than 100%. If you calculated something in one of your experiments and the efficiency came out as more than 100%, I would be doing it again because you've gone wrong somewhere. The other thing you could have said is, let's have a look. This goes up 2, 4, 6, 8, right? Electrical power input. So they increased the power 20 watts at a time. Here, the output power goes 10, 20, 30, 40. This should be 40. Okay, just from looking at the pattern in the results, you know that this has to be 40. So you could have said, comment on your answer, you could have said the power should have been 40. Now, suggest a reason for this anomalous result. Now this was, I think, more difficult because you had to say specifically what the reason was. Now, it's to do with the timer, right? Time taken. This time here is wrong. So everything here is fine. These two columns are fine. But this is wrong. So what happened with the time? Well, either they started the timer too late, or they stopped the timer too soon. Or if you wanted to say it in general terms, the recorded time is much shorter than the actual time. So let's say they started timer too late. Right, question 4. What is this? This is a relay. What is the point of it? Well, if you look at this circuit down here, the whole point of a relay is to keep a dangerous circuit, like a starter motor for a car. You wouldn't want to stick in your hands in a car motor because the voltage is high and it could electrocute you. If you've ever watched any sports in the arena, they have, so there's your football pitch or whatever, you've got these big massive lights that shine on the pitch to keep it bright. The person that goes and turns these lights on won't ever touch the circuit that they're connected to, because this will be very, very high voltage. They will press a relay switch like this. The relay switch will be a low voltage. They'll press it on. It will force these contacts together and it'll turn on the dangerous circuit without killing anybody. That's the whole point of a relay switch. Now let's have a look. I explain how turning the ignition key makes the current flow in the starter motor. So how do you get from turning that key here to this starter motor being on? Well, the first thing you needed to say is something along the lines of a current flows through the coil, or the current flows through the electromagnet. And that specifically, you've got to talk about current. Okay, a current flows through the electromagnet. You were allowed to say a magnetic field is produced for 1 mark. So you didn't have to mention current, but I think it's important. Now, if this was more marks, if this was a 6 mark, you would then have to say this produces a magnetic field, which you should have done anyway to cover all your bases, because you don't really know what specific part of knowledge the examiner's looking for in a 3 marker like this. So you should have then said produces a mag field, produced, but this is the same marking point. The second marking point is the iron arm, or the arm, this thing here. This is an iron arm, is attracted to the electromagnet, or the arm pivots towards the electromagnet. So iron arm attracted towards electromagnet. I like saying that the iron arm becomes an induced magnet, but because again it's a 3 marker, we don't need to go into too much detail. Then the third point is saying that it pushes these contacts together. So you're kind of understanding this diagram. So it's kind of hard to understand if I've scribbled all over it, so let's get rid of this. You're understanding this diagram and you're saying, okay, if this arm moves towards the electromagnet, this side pushes out, which then pushes these contacts together, which creates completes the circuit and allows the current to flow. So and then this pushes contacts together. And in the question they have said it makes a current flow in the starter motor. So you don't say that, they've already told you. They've told you this bit, which would usually come after that statement. Okay, so there's your 3 marks. Question 5. Why is iron used as a core? It's magnetic. Why is the wire insulated? Right, so I've got an iron core like this. There's my iron core. I have got my wire. Goes like that, doesn't it? Goes round the iron core. Round the iron core, round and round and round and round, and then it goes off to the circuit. If this wire is not insulated, what happens to my current is it flows in here, and then it goes, actually, there is a much easier path. I'm going to go that way and out. It will flow, the current will flow through the iron core if the wires are not insulated. Or if you've got it really tightly wound together and you've got 2 bits of wire that are touching and they're not insulated, it could just flow through the wire like that and completely bypass the coils, which is the whole point of an electromagnet. So, why is the wire insulated? To stop the current flowing through the iron core. Right, I'll go back to green. Right. This question, I'm actually surprised that many of us didn't really do too well on these calculations, because they gave us the equation. Some of you remembered the equation and could put some numbers in, but only for one side. You couldn't do it for the other side. So you'd say, you would calculate, say, this side equals a number, but then not use the other the other data you were given. Okay, so let's see. Now, this is a small step down transformer. So because it's a step down transformer, I know the number of turns on the primary is bigger than the number of turns on the secondary. So the number of turns on the primary has to be 20,000. The number of turns on the secondary will be 500. Okay, just from the question, right? Now, a part of the difficulty is you've got to figure out which is which. Now, luckily in the question they actually gave you the voltage. They don't have to, because you have to remember that the mains is 230 volts AC. Now, this is the voltage across the primary. Okay. They actually told you that you're calculating the voltage across the secondary, so it gave it away a little bit. It should be a 0. Voltage secondary. So let's put my equation out. There's the equation here. So I'm just going to write it again. So voltage primary over voltage secondary equals number of turns primary over number of turns secondary. Let's put my numbers in. So now we're putting the numbers in. This one can be red, so that's 20,000. Okay, this one can be blue. I'm going to make it thin. Number of turns on the secondary is 500 equals, and I'll do black for the voltage across the primary. So we've got 230 over. So this is that one. This one is that one. Just so you understand where the numbers are going or where they're coming from. Right? I'm just substituting the numbers in, and green can be the voltage across the secondary. So that is VS. Okay, you got 1 mark for doing this. Now, let's work out 20,000 divided by 500. That's 40. So I've got 230 divided by the voltage across the secondary equals 40. Now I need voltage across the secondary equals something. Now I'm not going to do the little mathematical trick I like to do. I'm going to just do it normally. So where's my pen? There it is. To get rid of the voltage, I do not want voltage on this side. It has to be over here, right? So I'm going to times both sides by voltage across the secondary. And what you'll find is this one and that one will cancel out. So now I'm left with 230 equals 40 times voltage across the secondary. How do I get voltage by itself? Well, then I need to divide this side by 40 and this side by 40, so that that and that will cancel. I am left with 230 divided by 40. It is 5.75. 5.75 equals voltage across the secondary. So there is my answer. That sounds reasonable. If you had a plug or an appliance for your phone, it would need to be low voltage, so you didn't, hurt yourself, and also it doesn't take a lot of power. So the answer to this one, 5.75 volts. Give the unit. You see that? If you wrote voltage or volts, you got 1 mark. This is worth 2 marks. Okay. Question 6. What is the name of the effect that causes the wire to move downwards? That is the motor effect. Suggest one change you could do to this apparatus to make the size of the force that the wire X experiences. Well, the easiest thing to do is get a stronger magnet. If you look at this, get a stronger magnet is the easiest thing to do. The other thing you could do is increase the current, but I'm going to say stronger magnet. Yeah, always the answer. Stronger magnet, increase the current. Figure 2. Now, we've done this before, so if you went back and you looked at your answer for the previous one, that's great. As long as you tried to figure out how you got the answer rather than just copying it in. The first thing that you need to do, right, it says show the unit, calculate the flux density. Hopefully you would remember the unit is Teslas. So a capital T or Tesla gets you 1 mark. Now, I've done this proof before, so I'm just going to go through it again very quickly. Let's see. So this is going to be an F equals Bill question. And it wants you to calculate the magnetic flux density. It's told you the current, which is there, is 1.5 amps. It's told you that the length of wire in X, which is the length of wire in the magnetic field, is 5 centimeters. 5 centimeters is 0.05 meters. F, they have not given you F. What they have given you is a moment equals 4.8 times 10 to the minus 4. If you used this as your force, you lost 2 marks, but you could still get 4 out of 6, which is a very good score still for a grade 9, grade 8 question. They gave you the length of this. Okay. So this is, I'm going to put this as distance. I'm going to call this distance because it's distance from pivot. And that is 0.08 centimeters. Now, new color. We should know that. So stage 1, we need to calculate the force. What is the force? Well, we need to know that a moment equals a force times a distance from a pivot. So even if you don't understand the setup that's going on in this, you can just go, right, I need this equation here. So my moment is 4.8 times 10 to the minus 4 equals F times 0.08. Now I'm just going to get my calculator again and try not to chuck it around my room. 4.8 times 10 to the minus 4. And I'm going to divide that by 0.08. And that gives me an answer of 6 times 10 to the minus 3. So force equals 6 times 10 to the minus 3. So there it is. That's in newtons. Now, using my equation, so let's change colour again, because now we're on to part 2. F equals Bill. I've got my force, 6 times 10 to the minus 3 equals, B is what I'm calculating. I know I is 1.5, and I know the length of wire inside the magnetic field is 0.05 meters, or 5 centimeters. Now, 1.5 times 0.05 equals this. So I've got 6 times 10 to the minus 3, so I'm taking it in stages still, 0.075. I need B equals, so what do? I divide both sides by 0.075. So 6 times 10 to the minus 3 divided by that gives me an answer of B equals 0.08 Teslas. So there's your... Okay, again, that is a grade 8-9 question. It should be the last question in the paper, but because it's a triple paper, they had a little bit of overlap. Now, next one. Again, using this equation, should have been quite straightforward. Just put the numbers in, get an answer out. So they give you primary core. Number of turns on the primary equals 800, which is there. It has that on the secondary, so number of turns on the secondary equals 12,800. Again, I know this is tedious, but this is what you should be writing down every time. The potential difference across the primary is 25,000 volts. Notice, so let's say, hold on, VP equals 25 kilovolts. That is not in volts. So what I'm going to do is that equals 25,000 volts. And what does the voltage across the secondary equal? Well, we don't know. That's what they've asked us to calculate. Show clearly how you work out your answer. Now, they've given me the equation upside down, so it means I have to rearrange. I'm actually going to flip it because if you remember, you can write it any way you like as long as you follow the rule of voltage is on the same side and primary and secondary are either on the top or the bottom. So I'm going to write voltage secondary over voltage primary equals number of turns of secondary equals number of turns of primary. That end is backwards. We're going to leave it backwards. Now, let's put the values in. My voltage across the secondary is what I'm trying to calculate. So I'm actually going to... right, so voltage secondary divided by voltage primary, 25,000 equals number of turns on secondary, which is 12,800, divided by number of turns on the primary, which was 800. Well, let's have a look. 12,800 divided by 800 equals 16. So I have now got voltage of the secondary divided by 25,000 equals 16, right? Because this fraction here, if you put that into your calculator, just equals 16. Now, to get the voltage across the secondary, I just do 16 times 25,000, right? Because then 25,000 times 25,000 on both sides, like this. That and that cancel. So 16 times 25,000 equals 400,000. Big number. 400,000 volts. Right. Makes sense. It says it's a very large step-up transformer. So it's stepping up to a massive voltage is good, because it's going to be on the power lines, it's going to be safe, and it's going to save a lot of energy loss. So there's your answer. Okay, B shows the structure of a transformer. Primary and secondary cores are made of insulated wire. Why is this necessary? You need to say that so the current is forced to go around the coil, or so the current does not flow through the core. Okay, so current does not flow through core. Why is the core made of iron? Well, magnetic. It is a magnetic material. Part 3, explain how the transformer works. Right, 3 marks, easy. There is an alternating current in the primary coil, sorry. 1 mark. Produces a, now this, you have to say this, changing magnetic field. If you do not say the word changing, you do not get this mark. This, again, this induces an alternating potential difference across the secondary coil. But you can just say this induces a potential. I'm going to write alternating because it's better. Alternating potential difference across the secondary coil. There you go. 3 marks. Give 2 advantages of the national grid system. A lot of you that answered this got it correct, really. Now, if you've got one place controlling anything, you have, like say, if you've got a national grid, it's easier to see where the supply and demand is. So it's easier to control supply, demand. Again, some people said about local stations breaking down, which is great. If local breaks down, then the national grid can supply. Okay, you could say electricity can be fed to remote places that are hard to get to. You could have said that fewer power stations are needed. Somebody even said that having the power stations away from like rural areas, or like towns and cities, means there's less pollution, which isn't in the mark scheme, but it's a good answer, so I gave the mark for that. Question 8. I'm actually going to show you the mark scheme for this before we answer it. So it says step up, step down transformers, describe the similarities and differences. You should include the details of construction and the effect it has. Let's have a look at the mark scheme. Right, I'm just going to show you this bit to start with. Right, 0 marks, no relevant content. A level 1 answer, which is 1 to 2 marks. It says either you describe the construction of a transformer, or you tell me what happens in a step up or step down transformer. So you can only get 2 marks if you just do that. A level 2 answer, it says there is a description of the construction of a transformer, and there is a correct statement of the effect of one type of transformer. A level 3 answer, which is 5 to 6 marks, says there is a clear description of the construction, and there is a correct description of how transformers, both of them, affect the input potential difference. Now, details of construction. If you talked about the laminated iron core, it's made of iron. There are 2 coils. They are made from a conductor. They are covered in plastic insulation. They are usually on opposite sides. Step up has more turns on the secondary. Step down has fewer turns on the secondary. This is information on the makeup or the construction. The effect on potential difference, saying that the step up transformer, the output potential is greater, and the step down, the output potential is lower. So a lot of you said about the number of turns of coil on the wire and what they did on the potential difference. So you got the marks for that. But you missed out on some of the obvious marks, like how is it actually constructed. So let's start with the easy thing. A lot of people started with step up has the output voltage is greater than input, and they said that for a step up the turns of wire on coil is greater on secondary coil. Okay, you then said that a step down, so I'll do this in red, tide of writing in green, down, the output voltage is lower than the input, and that again the turns of wire on the coil is less on secondary. So I'm literally just copying what I've written above, but I've changed it for step down. So these are how you're comparing them, and this is how they are different. How they are both similar. Both of them, they have a laminated iron core. They have insulated coils made from a conductor, usually copper. Okay, there is 2 coils of wire, and this is wrapped around the core. Now, that's everything. Now, a lot of people did this comparison here, so you got 3 or 4 marks. Okay, not many people mentioned what are both of them made out of, talking about the iron core, or talking about insulated coils, or the wire is made from a conductor. I know some of this is obvious, but the answer was in the paper because they had diagrams before. Chances are you wouldn't get that in the real thing, but there is your 6-mark answer. So green pen, and then email me your green pen, and that is our topic pretty much finished. We just need to do the spam.